the red light on? Yeah, you're good.
Oh, we're good? Okay. Well, good afternoon, everyone. I am Joel Bean, and I work with fractional calculus. Now, this might be intimidating, but don't be afeared, because it was originally proposed by Leibniz really very shortly after ordinary calculus in the 1700s. I want to start this talk with a very physical example, diffusion, right? We know diffusion can be modeled relatively well by the diffusion equation. If you have gas in some volume and you want to look at how it's moving, you can use this to model that. However, if you have something that's complex, like a geometry that looks something like this, then the regular diffusion would no longer work. We call this anomalous diffusion. Now, one of the ways you might want to fix this is by introducing a multi-scale potential that would cause the material that you're modeling to avoid the geometry. The problem is that's disgusting. If you think about writing a function that's going to do that, that's going to be terrible. So one of the things we can do is we can think very carefully about the dimensionality of the structure that we're looking at. And we can write a fractional diffusion equation that is much nicer and models movement of material through medium like this extremely well. All right, so now if we look at mathematically what fractional calculus is, I'm going to present you two ways of understanding it. First is using Fourier transforms. We, of course, can have the momentum operator in momentum space and position space, and the communication between those two is by the Fourier transform. If we take this into the fractional space, we have a nice straightforward generalization of the derivative being fractional. We can extend this quite cleanly to regular derivatives of functions. When we take the Fourier transform, all we have to do is multiply by this constant. We can do the exact same thing with fractional derivatives, and it generalizes again very nicely. The other way of understanding these is by using a discrete definition. You've already seen the regular derivative. We all know and love this one. You can generalize this quite nicely to any order of derivative using the binomial coefficient. Now, if we take this into the fractional space, this happens, which looks a lot like our ordinary derivative, except for one really important detail. Suddenly, we're summing to infinity. What this shows is the non-locality that's inherent in fractional derivatives. What this tells you is it's telling you you're taking an infinite amount of prior information from the function to be able to compute what the fractional derivative is at that point. Now, my work has been to develop and work with this integer order series that we use to understand and model fractional derivatives. So why did we build this? Because the fundamental laws of physics are based on ordinary derivatives, of course, not fractional derivatives. But what we want to do is we want to connect mathematically rather than empirically these fundamental laws to the fractional derivatives. How fractional calculus has traditionally been used has been very empirical. What the folks do is they'll take their coffee, spill it into the ground, and measure the diffusion of that, and then fit a fractional order to that, rather than developing it fundamentally. An example of where this might be useful is in higher order dispersion in the nonlinear Schrödinger equation. The nonlinear Schrödinger equation looks something like this. Notice that you have these higher order terms here. What we can do with fractional calculus is, instead of the traditional approximation of getting rid of these higher order terms, we can instead add an infinite number of higher order terms and concatenate them into a fractional derivative. Now, we built this integer order series from this. This is the definition that you already saw. All we have to do is take and put the shift operator in there. The shift operator takes the function and shifts it by a value h. What we can do is we can take this thing, Taylor expand it, and then shove it into the sum by doing this. Then we have a bunch of integer derivatives, which is exactly what we do, what we want. Now, you have to do a bunch of really disgusting sum math here, but you can eventually get it down to this nice expression. What does this expression mean? Well, let's break it down into three components, really. The first of them is the non-local derivatives. All of these initial order derivatives are where this non-locality I mentioned earlier comes from. The way to understand this is to think about finite differences. When we look at higher and higher order finite differences when we're doing numeric methods, each of them has to take more and more information from either side of the function to be able to compute the derivative at that point. In the same way, this encodes that non-locality inside of it. The other thing we have is fractional polynomials. This, of course, is fractional because we have k, which is an integer, minus q, which is not an integer. One of the ways to understand this, now that we see this, is an expansion of the fractional derivative in the basis of its ordinary derivatives multiplied by this fractional polynomial thing. The other thing, of course, is just a bunch of coefficients. This is the binomial coefficient, and this is the gamma function, but all they are is constants. And what's nice about these constants is they fall off quite quickly. This is, of course, the order of the constant, and this is the magnitude plotted on a log scale. So even at high values of the derivative order, we have low values for the coefficients when k gets pretty large. Now, these derivatives are important for linear and nonlinear waves. For linear waves, we use the cosine. And for nonlinear waves, we use the hyperbolic tangent because these are canonical solutions to the Schrödinger equation and nonlinear Schrödinger equation, respectively. Now, the linear wave, which is modeled by cosine, looks a lot like this. This is the 3/2 derivative that we computed of this. I have three things here. The analytical solution is in black, and then our approximation is in orange, and the Taylor series is in blue. Now, for the Taylor series, we took 10 terms, and for ours, we only took 3. How the Taylor series works is we expand the function in its Taylor series and then act on that with the definition of the derivative. As you can see, our approximation is much more effective than the traditional approximation when you get to large position. Now, the nonlinear waves are even better because they have a finite radius of convergence, which means that if you're out in this area, you can't even use the Taylor series to approximate it because it always diverges. The other thing we did to show the efficacy of our series is by looking at important fractional differential equations. First of these is a simple model of the Schrödinger equation. If you take the Schrödinger equation, remove the potential, and shove all of the constants into lambda, it looks like this. So what you can do with this is you can take it and put it into the series and then truncate at some order. We took it to second order and then truncated it like this. So we end up with an ODE that we can solve with numeric methods. We did the same thing for a step towards the stochastic Schrödinger equation, where we introduced this term right here, which if we wanted to have stochastic noise, we would make this random. And we did this for both the first and the second order ODEs. Now these approximations, the first one is great. We have a line that's right on top of the other one. It modeled very nicely. The second one is a bit more rough. What's interesting about it is we have much better convergence for the second derivative than the first, which is what we expected. But we also have this interesting activity of the different derivatives. The second order one looks kind of damped, while the first order one is not much damped. One way that we can understand this is by thinking very carefully about the odd and even terms inside of our series, which is one of the things we want to look at. You can think of it kind of like a Fourier series where we have cosines, which are even, and sines, which are odd. It acts a lot in the same manner at least conceptually. So the future prospects for this work are looking at those even and odd terms and trying to understand what they mean in terms of the fractional derivative, whether they cancel when you sum them, or whether they have specific meanings for each of them. Then we want to be able to build numeric methods to solve these fractional differential equations from our integer order series. Finally, we want to be able to simulate the fractional Schrödinger equation to understand quantum effects in multi-scale media. I'd like to thank my collaborators, Dr. Lincoln Carr and this flattering picture of Joshua Lewis. And then thank you for your time. I will take questions now.
Would you be willing to go back to the graph of the nonlinear function you were doing with respect to a Taylor series? Yeah, that one. Do you also have a graph with respect to the work you're doing? Because I know the one before, you had all three modeled together. Where's the...
Oh, the analytical solution? That's because it diverges a lot.
Okay.
Yeah. Yeah.
What if you take like let's say a differential equation, and for the order of it, you plug in some kind of like function of t or something like that. So it's a continuous function. What would the outcome of that look like?
That's a really good question. So what you can actually do with some of these multi-scale media is if the dimensionality or the macroscopic properties of that vary over space, you can make that order a function of space or a function of time if it varies with time to more effectively model things. Yeah?
Follow-up question. So when you're solving it's like differential equations like to the order of 1/2 or 3/2. Could you still use other methods of solving it like you do with integer ones, like product rule, chain rule, stuff like that?
Yes. So unfortunately, Josh is not here right now because he would be talking about both the product and the chain rule for these derivatives that we derived using our integer order series. But they get a lot more complicated and disgusting. But yes, you still have those rules. Yeah.
On the previous slide, you said that for the polynomial, the approximation of the Taylor series, you got a Laporte approximation with 10 terms, while your approximation only needed 3 terms.
Yeah.
What's the time complexity of your algorithm versus a Taylor series approximation?
That is something that I don't know offhand.
Okay.
It's relatively simple though, because all it is essentially taking derivatives, known derivatives of trig functions. Yeah?
What are the units of a fractional derivative even mean?
They actually follow very naturally. They're essentially the order. So if you take the derivative with respect to time to the alpha, then you would essentially divide by time to the alpha in the units of that. Yeah, Christian.
Following up to that, so like if you had time to the 3/2, because it's a fractional calculus, like what does that truly give you? I guess like what's the conceptual?
The best way to understand what it means is that it only really has meaning inside of a fractional or fractal geometry, because fractional calculus is very natural in fractal geometries. The problem is it doesn't really have any meaning inside of normal 3 space that we deal with. Yeah.
Thank you.
Yeah.
Sorry. What about when you take something to the order of like an irrational number, like pi or something? Does that still have physical application?
Yeah. So the thing to keep in mind is pi is just a number, and it might have some special implications in the fractional calculus world, but not necessarily. Yeah. Yeah.
Is the fractional definition of the factorial, does that use the gamma function?
Yeah, yeah. So gamma function is the natural generalization of the factorial.
Okay. So is there like a way to combine the gamma multiples?
Say again?
Well, you have a gamma function in your definition of a fractional derivative.
Oh, yeah.
Have the gamma function in your factorial.
So the gamma function comes from when you generalize the integer order derivative to the fractional order, your factorials all become gamma functions. Christian?
So you said fractional calculus has been around since the 1700s?
Yes.
Could you expand a little more on what, like, how you're trying to improve it from this point on?
So the problem with fractional calculus is it came about and then no one knew what to do with it. It just sat there because like it's kind of useless unless you have really specific applications like anomalous diffusion.
Okay.
And a lot of that didn't come about until you had computers because a lot of this is useful in numeric simulations. So what we're trying to do is not just be able to empirically do things with numerics, but also be able to understand what these things can mean when we're looking at actual mathematical stuff, using analytics.
All right, let's thank our speaker. Okay.